My name is Weiliang Yao. I'm a postdoctor of Professor Chen Dai's group at Rice University. It is my great pleasure to have this opportunity to show you our recent progress about the electric transport and low energy spin excitations of iron-based kagome magnet. First of all, I would like to thank the collaborators of this project, including group members of Professor Chen Dai's group and Professor Leah Morrison at Rice University. The neutron scattering experiment was collaborated with Professor Masuda's group at ISSP, University of Tokyo, and Dr. Feng Ye at Oak Ridge National Lab. And this work was also partially supported by the ICANN postdoctoral fellowship with Professor Spauch at the University of Tokyo. In the following, I will first briefly show you the background of this research, and we'll tell you the. Then we'll focus on the this interbeam ion germanium kagome magnet, and we'll show you the electric transport and the neutron scattering result. And I will finally make some conclusions and list the outlooks for future studies. The word kagome actually first used to refer to this kind of Japanese basket. It got the first round of broad interest is due to that its relevance to the quantum spin liquid physics. The Herbert-Smithite mineral has a copper-based kagome magnet, and with inelastic neutron scattering, people find that it has this kind of interesting continuous spin excitations in the brain zone. But more recently, people noticed that the electric structure of this kagome lattice is quite interesting, even based on the very simple tight binding calculation. For example, you can find the Dirac-Cohn Werhoff singularity and the flat band. So more and more people are getting interested in to this metallic kagome materials. Broadly speaking, there are three kinds of major kagome structure families. The first one is the binary structure, and the second one is the 166 structure, and the third one is the 135 structure. As you can see, that you can put a lot of elements in these kagome structures, so you will immediately get a lot of materials to play with. And fortunately, most of these compound can be grown into single crystals, so you can do a lot of experiments on this sample. And with this high tunability, the kagome material has been regarded as a platform for rich physics. For example, people in the past several years, people studied this ferromagnetic ion team, ferromagnetic terbium magnetic team, and this nominal anti-ferromagnetic magnetic team. And there are very interesting enormous Hall signals in these compounds. Due to this time, in these materials, there is magnetic order, and so it brokens the time reversal symmetric breaking. But to break the time reversal symmetric breaking, you do not necessarily to have the magnetic order. For example, in the 135 system discovered by Professor Stephen Wilson, you can see that there is still an enormous Hall signal. People interpret this phenomenon by this loop current picture. But more recently, there is another kagome magnet, kagome anti-ferromagnet shows the intriguing enormous Hall signal. The iron germanium has a canted anti-ferromagnetic ground state with the charge density wave order. So, the problem I want to address is that whether there is an enormous Hall effect can exist in a collinear kagome anti-ferromagnet. In the following, I hope that I can convince you that it looks so in this interbeam ion germanium kagome magnet. The ytterbium iron germanium belongs to this 166 type of kagome family, and there are only 6 members of this kind of kagome materials, and most of them have a nail temperature well above the room temperature. And the ytterbium iron germanium, for the structure of this ytterbium iron germanium, you can build by inserting this triangular ytterbium sublattice into this parent binary iron germanium compound. And the single crystal can be grown by a flux method. One particular feature of this ytterbium iron germanium is that it is the only member of this kind of kagome material have a spontaneous spin reorientation transition. From this magnetic susceptibility measurement, you can see that there is a clear feature of spin reorientation around 63 Kelvin. Above this spin reorientation temperature, the magnetic structure is an A-type AFM order, but below this spin reorientation temperature, the spin is canted away from the C-axis. From this resistivity measurement, you can see it shows a typical metallic behavior. If you do a derivative, you can see a sharp peak around this spin reorientation temperature. Next, we studied how it responds to an external magnetic field. Here is the magnetization measurement. Overall, this curve shows a linear behavior, but at a low temperature below the spin reorientation temperature, and in a small field range, you can see this nonlinear behavior. This nonlinear behavior shows some correspondence in this magnetic resistance. Above this spin reorientation temperature, you can see that the magnetic resistance is nearly negligible. But but below this spin reorientation temperature, you can first see some parabolic response, then follow up the linear response. But overall, this magnetic resistance is quite small, only about several percentages, up to 9 Tesla. But if you transfer to the Hall geometry like this, you can immediately see some interesting features in the Hall resistivity. First, at a temperature well above the spin reorientation temperature, the Hall response shows the linear behavior, and the transporter is in an electro-dominated feature. But when you close to the spin reorientation temperature, you can see that the Hall resistivity shows a very nonlinear behavior, and when you further go into the spin reorientation phase, you can see that the Hall resistivity shows that it was dominated by Hall transporter behavior, and at a high magnetic field about 4 Tesla, the Hall resistivity shows the linear behavior. According to this seminal paper, the Hall resistivity can be decomposed into 3 parts. The first one is the normal Hall resistivity, which is proportional to the magnetic field, and the second one is the anomalous Hall effect due to the magnetization, and the last one is the anomalous Hall effect due to antiferromagnetic response. The last part is the focus of this study, and to get a more quantitative view, we can transfer the Hall resistivity to the Hall conductivity, and by extrapolating the linear part, we can get this anomalous Hall conductivity, and by plotting the temperature dependencies of the Hall conductivity, we can see that the Hall conductivity disappears when the temperature is above the spin rotation. So the Hall response, the anomalous Hall conductivity is closely related to the spin structure of this magnet. So to understand
just silly question. What is the TSR?
TSI means the spin reorientation.
Okay.
To study the detailed magnetic structure, we use a neutron diffraction technique. Here is the two patterns, which is this one is above the spin rotation temperature TSR, and this one is below it. We can see overall these two patterns are quite similar. There is no incommensurate magnetic peak and no charge order peak appears below the spin rotation temperature. But if we check the temperature dependence of this 001 peak, we can see that the intensity of this peak suddenly drops at the spin rotation temperature. And for this 101 peak, we can see around 500 Kelvin. It shows typical order parameter behavior indicating the onset of the long-range magnetic order. So from these two patterns, we can conclude that the magnetic propagation wave vector keeps to be 0, 0, 0 for the canted phase. Since the charge order of this iron germanium has got a broad interest, it would be helpful to think about why there is no charge order in this compound here. Looking back to the iron germanium case, people found that the charge order there is due to the dimerization of this germanium atoms. They moved up and down. But in the 166 case, as you can see that the germanium has already been dimerized, so the crystal cannot further save energy by the germanium dimerization. This naturally accounts for the absence of charge order. Next, we go into the details of the magnetic structure. The magnetic structure can be analyzed by this magnetic representation analysis. There are totally 10 possible magnetic structures, but as we can see that for this one, it is the A-type antiferromagnetic order, which belongs to the phase that when the temperature is above the spin rotation. And for these two structure, it is planar. It is antiferromagnetic order, so they can also be ruled out. So we remain 7 choices, and for this collinear magnetic structures, if we calculate the magnetic structure factor, we can see that the 001 will vanish for this collinear spin arrangement, which is inconsistent with the experimental data. So the only possibility is that the canted intensity is contributed by this planar collinear magnetic structure. The final magnetic structure can be viewed by the combination of this of the A-type antiferromagnetic order and the planar collinear antiferromagnetic order. And the spins are in the AC plane with a canting angle about 70 degrees with respect to the C-axis. Having established this magnetic structure, we can think about the anomalous Hall effect have observed. From this magnetic structure, we can see that there is an inversion center, and so this magnetic structure has a combined spatial inversion and time reversal symmetry. And according to this but the intrinsic anomalous Hall effect is coming from the brain zone integration of this barrier curvature below the Fermi level. So with the existence of the special inversion and time reversal symmetry breaking, the anomalous Hall signal in this compound cannot be intrinsic, so there should be another reason for the extrinsic anomalous Hall effect. Actually, there are some proposals about the spin excitation-induced anomalous Hall effect. For example, in this serine, for this antimony doped serine tellurine and this magnesium germanium thin film, people propose that the low spin excitation may induce the skew scattering. But for this experiment, there is no direct evidence of such a spin excitation. To test the possibility of a spin excitation-induced anomalous Hall signal, we use the inelastic neutron scattering, which can directly probe this spin excitation. Since the crystal is quite small, we use a core-aligned single crystal array, and the experiment was performed at the newly installed cold neutral spectrometer at JRR3 Japan. We core-aligned the single crystal in the H0L plane, so we can access this reciprocal space. And at 2.5 Kelvin, we can immediately see that there is some capitalist spin excitation in the 001 point. And if we warm up, we can see that the intensity of the capitalist spin excitation gradually increase due to the thermal population of the Bose vector effect. But when we warm above the spin orientation temperature, about 63 Kelvin, we can see that there is a gap opening behavior. To more clearly see the gap opening behavior, we performed the temperature dependence at two energy positions. One is at this 0.55 MeV, another is at 2.55 MeV. We can see that at a low temperature range, the temperature dependence of these two energies are basically the same. But when the temperature is above the spin rotation temperature, the lower energy part suddenly drops, but the higher energy part continue increasing. And this is consistent with the onset of the anomalous Hall signal observed in this sample. So we consider that the gapless spin excitation at the brain zone center may provide a scattering channel for the extrinsic anomalous Hall effect. And it would be helpful to compare with other cases of ion-based kagome magnet. For example, for this ion tin case, its magnetic structure is a collinear magnetic structure, and the spin wave, however, in this case is gapped throughout all the temperature range, and there is no anomalous Hall effect. This provides some additional support for our proposal. And to summarize, we observed this anomalous Hall effect in the collinear kagome antiferromagnet ytterbium ion germanium, and it is closely relative to the spin rotation transition. And the gapless spin excitation at the brain zone center may provide us a source of the anomalous Hall signal. In the future, we will further explore the magnetization and electron transport at a high field, which is beyond 9 Tesla, and we will also study the ytterbium, the effect of the rare earth ytterbium sublattice, and will determine the full magnetic Hamiltonian by measuring the full spin wave spectrum. And finally, I hope that our study can motivate a comprehensive theory for free excitation-induced anonymous Hall signal. Thank you for your attention.
Thank you. Any questions? Yes, please.
Yeah, can you just go back to the last slide?
Last slide. Okay.
So it's very nice, very interesting system, but I'm a little bit confused. So do you happen to remember magnetic point group of this magnetic point group?
Magnetic point group?
Yeah. Do you remember? No. If you don't, it's fine. If you don't remember, it's fine. And then, do you know what temperature ytterbium orders?
The ytterbium actually does not order at least up to 0.5 MeV, 0.5 K.
0.5 K, ytterbium does not order. I see. Okay. I see. So that temperature you call spin reorientation temperature. So what is the near temperature?
The near temperature is about 500 Kelvin.
Oh, that's a much higher temperature.
Yes. Actually, we only covered this near temperature on the.
So spin state does change at that temperature, 80 Kelvin or something, right?
Yeah.
So
yeah.
magnetic point group does change from what to what?
Magnetic.
Maybe we discuss it later. Okay. Yeah. You know, this anonymous Hall effect is, magnetic point group is important. And
Yeah.
So question
Yeah,
is.
but I think since as you can see it actually breaks the C3 or C6 rotational symmetry for this.
Yeah, that's fine. That's fine. But
It will be lowered, I think, lowered much.
But what happens across that temperature? Spin flux transition. What happens?
It's canting, right?
Yeah, it's just a canting.
So
It was coplanar and now it's not.
You had another.
Correct?
you have it.
You had another slide where you showed different
Yeah,
temperatures.
this one.
And go back.
Yeah, so it's canting.
So even go back, you showed a whole variety of temperatures at which different
Too many.
magnetic order can find. Even before. Anyway, he had a whole range of temperatures at which the change.
So
right?
okay, maybe later on, but I'm curious about magnetic point group above spin orientation below, because anonymous Hall effect is very much magnetic point group is important, not space group. Magnetic point group is important.
Okay.
That's why.
So you had a question, right? Yeah, please.
Remarkable effort on the co-aligning of your 1,000 crystals. I was curious, at the very beginning of your talk, you showed this table of all the iron germanium 166 compounds. And there's something quite peculiar about, maybe.
This is the.
Right. If I look at the ytterbium site, you have the compounds that can have ytterbium, lutetium, scandium, 3+, magnesium, 2+.
Ytterbium is 2+.
Okay.
Ytterbium is not magnetic.
I see. Then
No. Ytterbium is 3+.
It's magnetic.
it's not magnetic.
It's not magnetic.
No, it's
Ytterbium
not
is not magnetic. Ytterbium is 2+.
Yeah, but according to older paper, I think by Paul Kelvin, they measured the X-ray absorption. They claim that it is 3+. But
Do you see magnetism from ytterbium?
up to now, no. We tried to measure high energy, for example, use inelastic neutron scattering to do the crystal field, but for this compound, it is very hard to get
So look, I
big.
can look at the lattice parameters and tell you that ytterbium is close to 3+, actually, you're right.
It is
Close to lattice parameters, it's close to 3+. Yeah.
But in fact, this was not my question. My question
Yes.
you have these 3+ valence, let's say at A sites, and then magnesium, titanium, zirconium, which will all be nominally 4+, hafnium, and niobium, maybe nominally 5+. This is very strange that you can put these very different species all sharing on that site, and I wonder, is there any understanding of the?
Yeah, but I think it just as Professor Wilson have answered for the question that it is a covalent system. So maybe you cannot use a full ionic picture to understand this structure,
But even in size, they're pretty different.
Yeah. But I think for this compound, for this series of compound, you cannot put very big atoms. For example, for this I think there is some less-than contraction. So you only can put this two. This lesson is bigger, but this side is small. So you can put this one, and also this elements, the radius are also very small, I think, comparing with the lesson series.
Ytterbium and lutetium are going to be closest in size to yttrium.
Yes.
So,
They're
Any
all
other?
clustered in size.
so you got your answer?
Mhm.
More or less, anybody have any question? So I have a very simple question. So how do you determine that the canting angle is 70 degrees?
We have some 4 neutron diffraction pattern, and different canting angle show some different relative intensity. So we can by fitting this stretch factor. Neutron diffraction directly probes this magnetic stretch factor, and we can calculate the magnetic stretch factor for different canting angle and compare with the experimental data.
I see, okay. Thank you very much. Thanks.